So what we want to do, this is the same graph as before. In this case, we want to just identify points of discontinuity. Okay, so discontinuity is happening, right here. Okay, there's a point of discontinuity happening here, here, at the asymptote here, and then the asymptote here. So there's 1, 2, 3, 4, 5 points of discontinuity. And we need to give an argument for the type for what this discontinuity is. Now, you don't really need to know the type, but the types here are, so this one is a jump discontinuity. Okay, this one's called a removable discontinuity. That's a removable discontinuity. This is an infinite discontinuity because it's just going along an asymptote. Same with this one. This is an infinite discontinuity. Okay, so the first one here, there's a discontinuity at x equals negative 1, 2, 3, 4, 5, 6. So at negative 6. And the reason why we can say this is that we can say that the limit as x approaches negative 6 from the negative side is not equal to the limit as x approaches negative 6 from the positive side. Okay, and this indicates that there is a jump discontinuity going on here. Okay, for negative 3, so we can say that limit as x goes to negative 3 of f of x, although it exists, it is not equal to f of negative 3. Okay, so the left-hand side and right-hand side limits do exist here, but the point is not there. So that means that this is a removable discontinuity when it looks like this. So here the limits don't match. Here the limit matches, but there's no point there. So same thing with negative 1. So we can just say the limit as x approaches negative 1 of f of x. Okay, it equals a limit. Okay, and we can actually say what the limit is. I mean, the limit is, looks like it's equal to 2, but it's not equal to f of negative 1, which is equal to 3. Okay, so these do not match. The actual point and the limit do not match, so it's again a removable discontinuity. So for the infinite discontinuity, we can write it like this. So left-hand limit as x approaches negative 3, as x approaches 3, is equal to negative infinity, and the limit as x approaches 3 from the positive side is equal to positive infinity. Okay, so this indicates that this is a infinite discontinuity. And lastly, this one here, this one we can just say that the limit as x approaches, what's that, 3, 4, 5, 6, 7, 8, as x approaches 8 of f of x is equal to negative infinity. But we have to kind of clarify that f of 8 does not exist. Okay, and this indicates that there is a infinite discontinuity there. Okay, so this one here, for this one, we may want to state that f of negative 3 does not exist. Okay, but that then tells us it's a hole with no point. There's a point not removed. But we're not going to be too picky about that for now anyways. Okay, so for the relative strengths of functions, if we have endpoint behavior at infinity, we can use this relative strength of functions. Okay, and here we have a strong over weak situation. Okay, the exponential function is much stronger than a quadratic function. Anytime we have a strong over weak, the limit is infinite. Here we have a very strong function on top, but we have an even stronger on the bottom. So we have, although it's not weak, it's just weaker. We have a weak over strong situation. And again, those are going to go to 0. So here we have weak and weak, but this is very weak. So it ends up the numerator is a stronger function and the denominator is a weaker function. So again, this is going to go to infinity. So it's important to make sure that you understand that this is only works when we have limits at infinity, okay, endpoint behavior. So this one here, this one's going to be, and maybe I can rearrange this and it might be a little bit easier to understand if we rearrange it. This is power 10. This is a square root, a fifth root. That's a, this fifth root is way more powerful, or the power 10 is way more powerful, but it's embedded inside a weak function. So we have a strong inside a weak. So it's kind of hard to, those contradicting terms. So we may want to just rearrange that so we can see that a little bit better. So we have here a weak root term on top, and I'm just going to use some log properties, and I have a weaker log term. Now, although it's times 10, it doesn't matter. That coefficient's really, as x gets really, really, really big here, okay, and again, remember we have the power of infinity, that 10 really is not going to be significant. This is still a really weak on the bottom and weak on the top, so it's just stronger on the top. So we end up with a strong over weak situation, so the limit is infinite. And again, I do encourage you guys to check these on graphs, okay? You should be checking these on graphs just so that you guys get a sense of how this works. You can check your answers for one thing, and then you can also check to see, you can get a sense of how these limits work. And having a sense of limits is very useful. Okay, so here we have piecewise functions, and we just want to check to see if they're continuous or not. So first of all, we should check the actual pieces of the function. Well, these are polynomial pieces. They are continuous. So then we only need to really worry about the points where they join. Okay? And we need to check for discontinuity. So we should really check for discontinuity at x equals 1. And, well, just really at x equals 1 between here and here and here and here. Okay? So let's check the limits. Okay, so the limit as x approaches 1 from the negative side, okay, so that would be this one here. Okay, so I'll just highlight that, of f of x. Okay, so if I plug 1 into here, I'm going to end up with 0. Okay, we see that f of x is equal to 0 at x equals 1, so that's all good, so it checks out. And then we should do the limit from the right hand side. Okay, so the limit from the right hand side, what's going to happen here? So we have the limit as x approaches 1 from the positive side. Okay, we're going to use this one here. We plug in the 1, and again we're going to end up with 0. This is all consistent. Okay, we have zeros all the way around, so we know it's continuous from here to here and to there, so this is a continuous function. Okay, so I'm going to claim that this is continuous. Okay, if I were to graph this, right, this is an upside down parabola. It's going to look like this, a parabola that looks like that. Okay, and then it's going to be the right side up parabola. That's actually just going to be in red here. Okay, we're going to have a point at x equals 1. Well, it's going to be at 0, isn't it? It's going to be at 0 here. Okay, so the graph is going to come up through the vertex, hit there, and then the bottom part of that graph is really just a parabola it's going to look like this, and then like that. So there's a parabola, blue parabola, and the other parabola is going to look like that. And the function is going to be this piece here is going to go like this and then bounce up like that. Taking a look at this piecewise function, okay, we want to check again the where the transitions happen. Okay, so first of all, check the graphs. This is a continuous function, continuous, continuous. We don't need to worry about the continuity within the function. We just need to check the continuity of these points that they join. So the limit as x approaches 1 from the negative side is going to be equal to 0. Okay, and the limit as x approaches 1 from the positive side is going to be equal to 1. Okay, so when I plug it into here, that's going to be equal to 1. Okay, so this is limits do not match, so it must be discontinuous at x equals 1. So discontinuous. Okay, so then we need to check the other transition point at x equals 3. So at x equals 3, okay, we're going to check the continuity at x equals 3. So limit as x approaches 3 from the negative side. Okay, plug in 3, that's going to be equal to 9. And I'm going to check it from the other side as well. So the limit as x approaches 3 from the positive side of f of x, when I plug in the 3, I'm going to get 6 plus 5. That's equal to 11. And again, because the two limits are not equal, we know that it is discontinuous. At x equals 3. Okay?